All right, in today's lesson, we're going to be looking at graphing rational functions. And the first example we're going to look at is the following rational function. R at x is 5x divided by x plus 4. Before we get started, what a rational function is a rational function is just a polynomial divided by polynomial. So in general, your rational function, let's say r at x, is defined to be polynomial, let's say p at x, over another polynomial defined to be q at x. We're going to focus our attention first at polynomials where the degree of the top and the bottom are equal. So you'll see here this polynomial has a degree of 1, and this polynomial also has a degree of 1. And that's going to be our first sort of focus when we're looking at graphing these rational functions, is polynomials of this nature. Let's take a look at graphing the following. So with the following polynomial here, the first thing we want to look at is finding some characteristics of the polynomial, like what's the x-intercept and y-intercept, vertical asymptotes and horizontal asymptotes if there are any. First of all, let's look at finding our x-intercept. If I want to find the x-intercept of a rational function, what you want to examine is when is the top 0? So if I take a look here, you'll see that the top is 0 when 5x is 0, or equivalently, x is 0. So right away, we have a rational function that has an x-intercept of 0. Anytime something crosses the x-axis at 0, that must mean it also has a y-intercept at 0 as well. So we know our y-intercept is 0 too. So I have a rational function with x-intercept and y-intercept both at 0. Now you want to take a look at your vertical asymptotes. Now if you remember, your vertical asymptotes exist when the bottom is 0. So the question becomes is when, if at all, is the bottom 0? Well, you set the bottom equal to 0 and solve, just as we did with our x-intercept, right? I want to know when is the top 0, set it equal to 0 and solve. Same thing with vertical asymptotes. Set the bottom equal to 0 and solve, to which we get x is negative 4. So now I have my x-intercepts, I have my vertical asymptote. I want to take a look at finding the horizontal asymptote. Now the horizontal asymptote, your function exists at the outer bounds of your function. So as x gets infinitely large or infinitely small. Let's take a look at computing this here. What you do is, first step is let's factor out the largest power that exists in the numerator and denominator. So in this case here, I can factor out an x, just leave me with a 5. On the bottom, I can factor out an x, leave me with a 1 plus 4 over x. And you'll see here, as x tends towards positive or negative infinity, we can see two things. The first thing we see is that the 4 over x is approaching 0, and we see that the x's can be canceled off. And again, the x is never going to be 0 itself, because don't forget, 0 divided by 0 is not equal to 1. Those do not cancel off here. But as x gets infinitely large and infinitely small, this might be a really, really small number divided by that exact same really, really small number. Or you might have a really, really large number divided by that exact same really, really large number. In either case, you can cancel these off. Canceling off, I end up getting that r at x is going to equal 5 over 1, which in this situation reduces to become 5. So therefore, I have a horizontal asymptote at 5. Let's summarize all the information we found and graph our rational function. All right, so we got everything summarized here. I have a vertical asymptote at negative 4, so let's make that somewhere about here. I'm going to label that with x is minus 4, and a horizontal asymptote at 5, so I'll go ahead and label that here. And this is going to be y is 5. I have an x-intercept and y-intercept at 0. And now we've got our graph label for ourselves. Okay, now if I want to graph this function here, you'll see that you focus your attention typically on your vertical asymptote. And as my function approaches the vertical asymptote, either I'm approaching from below or from above. Those are the two options. Either x is, like as I approach my negative 4 from the right-hand side, let's say, there's either two options. Either you're going to tend towards negative infinity or tend towards positive. So essentially what we want to know is, as I pass by this 0 and I'm going this way, am I above or below the x-axis? So that equates to, what we could do is just pick a number between, this is negative 4 here, this is 0 here, pick a number between negative 4 and 0 and sub it in. So for instance, if I sub a negative 2, let's say, into this expression, the top will be negative, the bottom will be positive, to which the product of those will be negative. So that means that this function between here and here is below the x-axis. So therefore my rational function must tend towards negative infinity, and then you go towards your root, and then we approach our horizontal asymptote. On the other side of the vertical asymptote, things are a little bit easier. You'll notice that I don't have any x-intercepts here. So if my rational function was approaching negative infinity as I approach -4 from the left, the function would have to look something like this, to which we need another x-intercept, and I don't have that. So the only option here is the function will have to look something along these lines here. I'd have to, as x approaches -4 from the left, my function would have to approach positive infinity this time. And we have our rational function here graphed. Let's take a look at another example. So taking a look at our next example here, again, we want to find the same characteristics as before, x and y-intercepts, vertical and horizontal asymptotes. The first thing we must do when we're given a rational function is to see if there's any factoring and cancellation that can occur. You'll notice right away that in the bottom here we have difference of squares, and you'll see that the x minus 1s can cancel provided that x is not equal to 1. So therefore our function r at x can be simplified and rewritten as 1 over x plus 1, given the fact that x is not equal to 1. So what we have here and what we've created is what's called a hole. This hole is a point of discontinuity in which the function r at x is undefined. So now that we simplified our expression and identified the point of discontinuity and made note of the hole in our graph here, we're going to have to go ahead and find our x and y-intercepts and vertical and horizontal asymptotes if they exist. So to find the x-intercept of this function, the x-intercept happens when the top is 0. You'll notice we're not working with our original function here. You want to work with your simplified function, and the top can never be 0, so there is no x-intercept. If I go to find my y-intercept happens when x is 0. Evaluating this function at 0, we end up getting here 1. To find my vertical asymptotes exist when the bottom is 0. The bottom is 0 when x is minus 1. And lastly, to find my horizontal asymptotes here, if you'll notice, as x gets infinitely large, you can see that your function r at x will be approaching 0. So this has a horizontal asymptote at 0. And again, if you're having trouble seeing that, just pick numbers that are really, really large here. You'll be taking 1 divided by 100,000, a million, 10 million, etc. That'll approach 0. Or on the other side, as x approaches negative infinity, as I pick numbers that are very, very small, if you were to evaluate x at r at negative 100, r at negative 1,000, r at negative 10,000, etc., you will too see that these will approach 0. Let's put this all together and graph our function. All right, go ahead and graphing this here. We have here, first thing I would do is graph my vertical asymptote. I have a vertical asymptote at minus 1. Let's go ahead and plot that. I also have no x-intercept, but I do have a horizontal asymptote at 0. Let's plot that. So now we've got a horizontal asymptote at 0. I have a y-intercept at 1, so somewhere about here we have our y-intercept, and I want to go ahead and graph this function. So the same sort of idea, if we take a look to the left of minus 1, I don't really know, does the function look like this or does it look like this? There's a very easy fix for this. The only thing we have to do is pick a number in this interval, so in this case here less than minus 1, let's say we pick a negative 10, and if I were to sub that into our function here, you'll find the output is negative. So this is below the x-axis, so it's going to look like this. Now on the other side here, it's the same thing. We don't not have an x-intercept, so I cannot cross the x-axis, and my y-intercept is up here. So the only option for myself is it must look something like this. Now there's one thing we forgot, one thing we've omitted, is I have a hole in this function at x equals to 1. So we should go to our actual graph, go roughly where you think 1 is. Maybe this is x is 1 right here. And what we're going to do here is roughly at that spot here, we'll put a little circle in the graph. You can even label that further. And we can say this is a hole at x is 1. So you have this one singular point of discontinuity illustrated right here, and that's our hole at x is equal to 1. All right, that concludes today's lesson on graphing rational functions. Thank you.